everybody. So, I'm Massimiliano Mantione, and I'm here for this talk about how much performance you can get out of JavaScript. Now, again, about myself, something I've worked on in the past. I'm mostly a just-in-time compiler engineer, so this thing I did the most during my professional life. I've worked in the Mono just-in-time compiler, the Unity game engine, and the V8 team in Google for 1.5 years. Now I am full stack developer at Hyperfair, where we do a virtual reality platform. Now, about JavaScript performance, the point is, does it matter? Yeah, of course it does. But let's ask a better question. Now, does JavaScript performance matter to you? Well, it depends on the application you are developing. So, something else. Should I know how to write high-performance JavaScript? Well, again, it depends. It depends on what you do. But now we are getting there with the right question. Should I know the potential of JavaScript performance? And now, this is the correct question. Because the point is that if you don't know the potential of JavaScript performance, you cannot imagine anything new. Because you don't know if it's feasible. You don't know if you imagine something and you say, is it doable or not? Will JavaScript be able to do it or not? So how do you know? Because, for instance, would you imagine adding a neural network working in real time inside a web app? I mean, it might be interesting for certain use cases, but how do you know if it's feasible or not? So, to try to see if we know things or how we know things or how we can know things, let's start with a simple problem. So the simple problem is finding the first 25,000 prime numbers. It's just a computation, nothing special. So the algorithm is something like for x from 1 to infinity. If x is not divisible by any member of an initially empty list of primes, well, add x to the list of primes until we have 25,000 elements. It's just, really, it's not the best algorithm you can think of. It's just something so that you can see what happens. How fast will it be? And the point is, how do I know? So we say, let's experiment. And to experiment, we need some kind of baseline. And so we say, we have two contenders. A JavaScript program, now don't bother about the code. The code is exactly what I explained in pseudocode before. It doesn't matter. And another contender, a C++ program that does exactly the same thing. If you look at them, they almost look like the same. So they are really just the same program transcoded manually, of course. So I would say, let's race. Now here we have the programs. I have a script that should run the demo. So the first thing we do is we compile the C++ program to get the executable. And then we run it. And we say that it took 1.5 seconds, sort of. Okay, the numbers are in milliseconds. Every number is in milliseconds. Now we run this program, which is our first version of this program in Node.js, and it took, well, 6 seconds something. So we do a bit of maths and we find a ratio of 4.55. It's something like that, which means that we did this race, and now we know that C++ is about 5 times faster than JavaScript 4.5, whatever. And I guess it's not so bad. I mean, one is a compiled language, the other is interpret. It's supposed to be, and I would say, of course it's so bad. It shouldn't be like this. You deserve more, and you shouldn't give up. You should demand faster from JavaScript. How much faster? Now, how much faster? 3 times faster? 30 times faster? Do you think it's possible to make that program 30 times faster? How many of you think it's possible to make it 30 times faster? No? You are unfaithful. Boys, 300 times, 3,000 times. And the problem is, how do we know? So now we have a baseline. Now we know C++ does something, JavaScript does another thing. But how do we know what's feasible? Again. And the point is we need to be prepared. We need to know what to expect. So we need to know how the virtual machine executes and optimizes your code. And know how to inspect what's really going on, because you can guess what's going on, but then you should prove that your perception was true. And you should also know that you will never guess it right before you experiment. That's the first rule with performance. You can think whatever you want. You're going to get it wrong. So now let's go understanding how V8 optimizes JavaScript. Now this talk is about V8 because I've worked on V8. In the end, all the other major engines are doing sort of the same things, and the advices I'm going to give you will apply to every engine. But now we are focused on V8. So first of all, we should know what is optimized code, because we are talking about optimized code, and what does it mean? Well, there are several steps. So the first thing is you can have an interpreter, and each JavaScript operation, if you are using an interpreter, have lots of branches in the machine code to say what's this operation. So if you are interpreting, you see the operation as a program, and you say, oh, is this an addition? Is this a subtraction? Is it a method call? Is this? It can be whatever. So it takes a lot when you have an interpreter. Now you could have a fast JIT. It is a machine code which calls eventually slow generic operations. So it's essentially a bunch of machine instructions where for each instruction you call the right JavaScript operation. So you don't have lots of branching, but then the JavaScript operation is not really optimized. It still has to do a lot of checks. Then you can have just-in-time compiled code, but with some kind of type information. So it's still like the code that I was explaining before, but every call to the operation is specialized. It knows what to do from the beginning. So this is faster. And finally, you can have an optimizing JIT. So it's machine code like the above, but cleverly optimized sort of more globally by a compiler, a proper compiler. And the point is, why do we do all these things? Because the last JIT is very slow. So you cannot do that for every piece of code you're going to execute. You need to balance trade-offs. So in order, I think you have noticed that in this list, we are always talking about type information. So if you do things generically, we are slow. If you know what you are dealing with, we are fast. So the point is that the virtual machine tries to define hidden classes inside your data. And these hidden classes will help the compiler, because no type info means that there are no optimizations. And in JavaScript, you don't have type info. The language is dynamically typed, which means the interpreter has to guess what's going on, see, check, and do a lot of operations. But with type info, it could be faster. And how much faster? Like C++? We still don't know. So the point is that V8 internally creates hidden classes for objects at runtime. And the point is that objects with the same hidden class can use the same optimized code. So just to see an example, let's say code like this. So we have a function, point, that produces a point, and the point is an object that essentially sets two properties, which are the coordinates, and that's it. Now, if we create P1 calling this function, then we have a point with these two properties. If you create P2, then we have again a point with these two properties. But then, if we take P2 and we add another property, then the shape of this object will be different. And this is a change that the compiler will have trouble dealing with. So we need to learn how to avoid the speed trap. Why this speed trap? Because the point is that the analogy is you want to run fast, but if you see a speed trap, you have to slow down, otherwise you get a ticket. And then you need to go slow for a while, and then you can go fast again. So the rules for avoiding the speed trap will be a lot, and will be all listed here. And in this case, the idea is you need to initialize all object members in constructor functions, all of them. Never add them afterwards. And you always need to initialize all of them in the same order so that you are sure that your objects have exactly the same shape. Now, another thing is about numbers. So we very often have numbers in our programs. And the point is that objects and numbers are very different. And JavaScript can mix them freely. So V8 uses tagging. Essentially, the trick is that pointers in machine code are numbers. So you can have a location, and you can store either a pointer or a number there. And there's a trick. So since pointers need to be aligned, because otherwise machines go crazy, they just cannot work properly. Essentially, the lower bits of the pointer are useless if the value is a pointer, because there will be 0 anyway. So what V8 does is use the lowest bit as a tag, and it's 1 if the number is a pointer, and it's 0 if the number is a number. And these are called small integers, SMI. Why small? Because suppose you are on a 32-bit machine, it's like having a 31-bit integer, because 1 is for the flag. So they are sort of smallish values. They are called SMI. They are ubiquitous in the execution of programs in V8, because every location could be either a pointer or a number. This is an internal trick. Now, what does it mean? It means that you should prefer numeric values that can be represented as 31-bit signed integers. Because if you overflow 31 bits, then the machine will have, the virtual machine will have a hard time fitting that number somewhere. It will have to fit it elsewhere, build other pointers. So this is usually happens. I mean, if you have a normal loop, a cycle, the length of something, the number will be slow enough. If you care about performance, just be sure that it will be slow enough, and everything will be fine. Now, about arrays. So in JavaScript, the distinction between objects and arrays is sort of subtle. They are objects anyway. So, okay, there is the isArray test, but you handle them sort of in the same way. You have square brackets, and you go inside them with square brackets. They really look the same. But in the implementation, they should not be the same, because physically they are very different. And the idea is that the virtual machine can see if you are using a compact set of keys. So if you've got an array and the set of keys is contiguous from 0 to the length, and they are all used, then physically this will be an array, sort of like a C++ array in machine code, so a contiguous chunk of memory. But if on the other hand you really want something that is more like a hash table, well, just use it like a hash table, and that's fine. The virtual machine will see that it's not contiguous, and then it will just build a hash table in memory, and that's okay. So again, to avoid the speed trap, if you want the fast elements behavior, you should really use this linear storage and use the indexes properly. And otherwise, it goes in dictionary elements mode, and you've got a hash table. Now, look at this. We have code, it creates an array. You have this array A, and then it does a loop where inside the first element of the array, it's using a bitwise operation. And this is a problem. This is a problem because that element was undefined in the beginning, which means that the JIT gets confused. You had an element that was undefined, and now you're handling that as a number. So the JIT is thinking, oh, this was an array. But what were you storing inside this array? How should it be shaped inside? He doesn't know. Now, if you do it like in the second piece of code, you create the array, and you initialize the first element as a number. And then, inside the loop, you handle that as a number. Now, that's much better. It's 2 times faster. So, again, about arrays, to avoid the speed trap, you need to use contiguous keys, starting from zeros and going on. You need not to pre-allocate large arrays, possibly, because if you pre-allocate an array that is too large, the JIT is going to say, well, you're going to waste too much memory. So it's actually not going to allocate all the array. So just allocate it one chunk at a time, that's fine. And you never, ever, ever have to delete elements in array, especially numeric arrays. And you don't need to load uninitialized or deleted array elements, because then again, the JIT is saying, well, there are holes in this array. If there are holes, I cannot really handle it uniformly. It should not be an array. And about specialized array elements, the point is you can have them. An array of pure doubles is actually very fast if it is all an array of pure doubles. So it needs to stay that way. So you can do mathematical operations with arrays. Just keep them that way. And in general, the point is that the JIT tracks the hidden class of an array, and inside that it tracks the element type. So it can build the proper buffer. It's a buffer that stores double values or integers values or reference values or whatever, and it will work properly. But just don't mess with that. Don't confuse the JIT. Because unboxing, like storing objects in an array of numbers, will mess things up. So in this code, for example, this is really the bad way. You create an array. Now, you store the first element, and this allocates a small buffer where each element is meant to be an integer. Then you store another element, and you say, oh, wonderful, I'm filling the buffer when you store index 1. So the JIT is happy. Then you store the third element, and it's a double. And it doesn't fit, because a double is 64 bits. So it's not the same thing. So it needs to reallocate the whole array. Well, it's small, okay, but and then convert. And now you put there a fourth element, which is a Boolean. And technically, a Boolean is an object, technically, which means that it will reallocate the whole array again and convert it again. So just don't do it. If you really, really want something like that, do like at the bottom. You do with a literal. Because if you use a literal, the JIT will see all the elements at once and will know. So it will be the right thing from the start. Now, why on earth do you want to do something like this? I don't know. Because this should be an array, should be uniform. But if you want to do it like this. So again, avoiding the speed trap. And you should initialize array literals. So use array literals for small arrays. Because if you do that, the JIT sees the whole array in one shot, and it can just do the right thing from the beginning. And you should pre-allocate small arrays to the correct size. So as I was saying, large array like more than 64 kilobytes, don't pre-allocate them. It's bad. But small ones, it's good. Because then you will avoid allocating something like 8 elements and then 16 elements and then 32 elements and then 64 elements, because this is what the JIT will do if you fill them one element at a time. If it is, let's say, not huge, small enough, just pre-allocate it if you know, and then you will avoid lots of reallocation, which are expensive. Of course, don't store non-numeric values objects in numeric arrays. I will repeat it a lot of times because it's so important. Now that we know how to store the data, we should say, okay, fast JIT or optimizing JIT? Well, historically, V8 had 2 engines. So it's V8, one engine, but with 2 engines inside. There was the full compiler, full gen, and it can generate sort of good code for any JavaScript. Then there is the optimizing compiler, crankshaft, that produces, let's say, great code, but really great code for most JavaScript. Now, the fast compiler is a full compiler that starts executing code immediately. And it quickly generates, well, good code, actually not so good, but very, very fast. And it assumes almost nothing about the types at compilation time, because it cannot know. It's the first time that the code is executed, so it can have no clue about what values will be there. So it has to do the most generic thing possible. And then it uses something that's called inline caches. What's an inline cache? It's a small piece of code that is meant to handle types efficiently, even in full gen, so the generic JIT, the fast one. And it's a small piece of type-dependent code for every operation. And what it does is it validates assumption and then does the work. And it can self-modify itself. So you have machine code that modifies itself at runtime. Now, this is the funny thing. Now let's see an example. This is actually an example from that program before of the prime numbers. Now let's just consider a small operation. So it's the modulus of these dot primes. Okay. Now the inline cache code, sorry, is, let's see if I have the mouse. Okay. It pushes something on the stack so that it can work with that. It pushes the argument, it moves things around, it moves things again, and then it calls this thing. This call is this dot primes. So this dot is actually this offset. So here is the this, and then it again does something, and then calls the initialization, and then it calls again. What you are seeing is that 3 function calls: the initialization of the inline cache for the square brackets, and the initialization for the inline cache for the modulus. So it's a bunch of function calls. It's totally generic. This thing cannot go wrong in any possible way. But for those operations, it's doing function calls all the time. So it's really not the best thing you could do. But the point is that over time, it will notice the type of things, and so it will patch the calls to invocations to specialized pieces of code that do the right thing immediately, which means that over time, it will become a bit smarter and it will do the right thing immediately. Now, at this point, there is still time to change the code back. So if the type of things changes back and forth from one type to the other, the inline caches will adapt, remember the sequence of types, sort of. So it will have some kind of view of what's going on over time. Now, what happens is that over time, this code will become hot because it will be executed a lot of time. So when the code is hot, there is a profiler, of course, inside the virtual machine. And when the code is hot, it will say, okay, it is worth to optimize it fully. So let's invoke the other compiler. And actually, the other compiler, now I want to introduce one more thing. Actually, there are more engines. Because over time, V8 gained 2 more engines. So now it has 4. And then the 2 old ones will be thrown away. But they couldn't just do a full rewrite. So what they did was build 2 more, have all of them, and then transition them. This is a funny story. But one is called Ignition. And it is an interpreter for memory-constrained device. So inside V8, the hallmark was we never interpret, we always JIT. And it was sort of okay for performance, but if you are short of memory, all that machine code is really heavy on performance, because even just wasting memory is heavy on the cache. And if you know how processors works, the cache is important. You don't have to waste it. So for small cell phones, it's very, very important to have an interpreter. And at that point, you can just build a very good interpreter and use it anyway at the beginning so that you start faster. So it's called Ignition because it starts fast. And then there is Turbofan, which is an optimizing compiler even more sophisticated than Crankshaft. Inside, it's really incredible. It's using some kind of state-of-the-art compiler technology. It's something like the most sophisticated C++ compilers, literally. Of course, Turbofan is lower, so it kicks up afterwards, like a turbo. So the old pipeline was that you have source code, you have the parser produces the internal representation, and it goes to full code generator, which is the slow one. And then eventually it's optimized with Crankshaft or with Turbofan. This is the pipeline with all the engines. Or eventually, there is this bytecode generator so that you can have Ignition, and the bytecode feeds information into Turbofan that again generates machine code. But this thing is going to become just this: source code, parser, internal representation, bytecode, and the bytecode goes to the interpreter, so you can interpret. His ignition isn't shown here because it's not a compiler, it's an interpreter. But then the interpreter collects type information just like full-gen did with the inline caches. That's the idea. So the interpreter checks the types, remembers the types, and so turbofan does have type information and can produce good machine code. And the pipeline of turbofan, well, that's huge, just turbofan. And it's funny because it has a lot of entries. So you can have the AST, or you can have bytecode, and you have graphs. And then you have a lot of steps to progressively optimize the code, and you can have a machine graph. And note this thing. Here you have the WebAssembly compiler. It takes a shortcut. Since WebAssembly is typed like machine code, you don't have to do all that stuff. You just say, okay, I know what this is like. So let's just go directly to the machine graph. And then you have even more, let's say, steps that tune the machine code at a lower level. And finally, you go here. And notice this, code stub assembler. This is an incredibly clever thing. This is actually ignition. So I just want to tell you this because it's not really useful to you, but interesting to know. The V8 team had this problem. They needed to make the interpreter. Now, how do you write an interpreter? You either write it in C++, but then the interpreter needs to interact with the code that has been emitted by turbofan. So you have C++ code that needs to be structured like the machine code produced by turbofan. It's very difficult to write. Or you can write the interpreter in machine code, which is a hell of a job, seriously. So they had this idea. They have, okay, we already have an abstract assembler. Essentially, turbofan is able to emit machine code to describe every possible JavaScript operation. So we will use turbofan to emit the machine code for every possible JavaScript operation, and we have the interpreter use that. That's the clever. So essentially, the interpreter is written at high level in C++, but at low level, it executes JavaScript using the machine code produced by turbofan. And this machine code is compatible with the turbofan one, obviously. They are interchangeable. So the code abides always to the same rules, which means that the pipeline is sort of funny because you can create machine code for turbofan starting from here, which is ignition. Well, okay, I wanted to show you this. It's fun. By the way, all these things I've just looked up because I like the thing. I didn't work on this because these things, they were just up in the air in 2012, 2013 when I was there. We were just discussing them. And it took something like 5 years to actually build all this thing. Okay, now let's get back to what happens with type information. And I call megamorphic attack because operations are called monomorphic if the hidden class is always the same. It has always the same shape, so monomorphic. Otherwise, they are polymorphic. And the idea is that monomorphic is better because the machine code for a monomorphic operation is very specialized and very fast. And internally, we call it megamorphic, the operations that continued to change from piece to piece and they were simply not handleable. Like here, you see, we've got a function that is called add, and internally it does x plus y, add. And you invoke it passing integers, and the plus internally becomes, I am a plus that works with numbers. And then you invoke it like in the second time with strings, and then the plus becomes polymorphic. That plus is not going to be optimized properly because since the compiler knows, oh, I can expect either numbers or strings. So it needs to call the generic operation anyway, which is bad. So this is the point, which means to avoid the speed trap, prefer monomorphic over polymorphic. So the idea is never change the shape of things. And by the way, this is a funny Redux issue. When you work with Redux, typically you create a lot of objects with literals and or with the spread operator. Eventually, you end up with exactly the same object, but the order in which the members appear in the object is different if you use the literal or the spread. And so they have different hidden classes. Now, this doesn't really matter in practice, because usually a React operation with Redux is not really CPU bound, so this is not a big deal. But it's important to know so that it can happen, and you should be consistent. Always use exactly the same kind of statement to create the object, so that it always ends up being the same thing. Sorry. Now let's talk about the optimizing compiler. As I was saying, the functions are compiled with this optimizing compiler, and type information makes the code faster, and operations are also inlined, and the monomorphic calls are also inlined. And the nice thing is that inlining enables other operations, because once you have a bunch of machine instructions all in one row, the compiler has more visibility and so can enable even more optimization. So this is really a full compiler. And this is the same example as before, but the same operation as before, but after the optimization. And if you look at that, you essentially don't have calls anymore. And there are a lot of compares that says, okay, is this reference here is essentially the pointer to the hidden class. So it checks, is the hidden class the right one? Now, this move with this offset goes from this to this dot primes. And as you can see, it's just like in C++. You have a pointer, and the property is just a few bytes away. So it's very, very fast, the access. And then you need to testing the flag. Is this a SMI or a pointer? Because you really need to know. And then, is the hidden class an array? Because primes needed to be an array. So it needed to be a pointer, and a pointer to the correct kind of array. And then at that point, you load the array length, convert the SMI length to an integer, and then check the array bounds. This compare operation is check for array bounds. And all these jumps, they are executed if the comparison goes wrong. So if the comparisons go wrong, well, the optimized code isn't good anymore. But if everything goes okay, you've got exactly the machine instruction for the load, a single one, and then exactly the machine instruction for the modulus and for the division. So that's it. This is the only overhead here are the checks that check that everything is going okay. You must put them there. There's no way to okay, actually with turbofan, it speculatively puts those checks elsewhere more out of bound. So it's even more clever. But let's say the checks are there. So another thing is that with turbofan, there will be no more what were called bailouts. So with crankshaft, there were some constructs like try-catch or generators. They could not be optimized. The good news is that turbofan can optimize everything. So don't worry about this anymore. And the problem is the optimization. This is still going to happen, of course, because I showed you that code. All those jumps. If this goes wrong, I go there. Where do you go? Well, you get back to the unoptimized code. The optimizations are speculative. The compiler is hoping that you will keep everything with the same types. It's a guess. Usually they pay off. But when something goes wrong, there is a de-optimization, and it throws away the optimized code and gets back at the right place, either in full gen or ignition, according to where you were coming from. And this is really, it's expensive. The amount of things that happen inside the machine when you have a de-optimization is catastrophic, literally. So try to avoid that. So avoid hidden class changes. And the funny thing is that here, if you use something like TypeScript or flow type, they actually help you. Because the coding style, when you're using those type checkers, is that the type of thing stays the same. So the point is, these do not have a performance benefit directly, but they do have it indirectly, which is sort of fun. Now we know our tools. Now we know how V8 works. We should know how to actually use the things. So there are flags to pass to use the profiler. This is in Node. And you can log what's get optimized with options like trace opts, trace the opts. And you can pass these options also to Chrome, so that Chrome as a process logs those things. So you can also inspect V8 inside Chrome if you want. It's a bit clunky, but it's doable. So at this point, I would say that you prepared. You should know that the problem is JavaScript. You should reduce it to pure JavaScript, no DOM, because I'm talking about JavaScript here, not DOM. So there are CSS performance problems, re-render performance problems. Those things are totally different beasts. Now you have to collect metrics. So run the thing and see what goes on. And you have to locate the bottlenecks and then fix the problems. So they say, let's make it faster. What does it mean? Well, it means that we are still in this example. We have to make it faster because we are not happy with being 5 times slower than C++. This is not good. So let's fix this thing. First of all, we have to run the profiler. Now I did it, and this is the problematic profile data. Sorry, it's okay. Maybe it's better, but anyway, you have screen problems. But if you look at this, what you see is that there are a lot of ticks spending in normal code, but I have to find it. Essentially, we have a lot of ticks spent in C++ code, in mod finite, in fmod something. So there's something fishy here. I was expecting a profile dominated by JavaScript code, and I'm seeing a profile almost dominated by C++ code. Now, investigating this is tricky. So I want to spare you all the logs because of time. But if you see what's really going on, you can see that there was a small bug in the code. This diff shows you the bug. Essentially, the comparison was with the equal sign here. And this thing was loading an uninitialized array element because the array was pre-initialized. It was 75,000 elements. But the array of primes is filled, and there is a counter counting how much you have filled it. And the point is, in this comparison, I was always going past 1. And this was driving the just-in-time compiler crazy, essentially. So let's patch it. And now, after the patch, this is the code. So you can see now that it's OK. Oh, we are in VI. Now we run the fixed one, and you see that it takes 1.3 seconds, which means just doing that silly thing with the array has been catastrophic. Now, 1.3 seconds, let's look at the profile data. Now the profile data is OK. So now everything is dominated by JavaScript, the proper functions. And if you go to the C++ section of the profile, it's almost nothing, which means this is the profile we expect. There are no more bottleneck or strange things. But 1.3 seconds. Now let's execute the C++ one. 1.4 seconds. Now what's going on here? I mean, and which means we run it again. Those are the numbers. We do the ratio. It seems that we are a bit faster than C++. This shouldn't happen. And actually, the problem was that we didn't optimize the C++ code. So sometimes really, you have an assumption, but it's totally flawed at the base. So now we are optimizing. You see the -03. This is the maximum level of optimization for the compiler. And now we run it again, and now it's, well, 800 milliseconds. So now the performance ratio is something like 1.55. But there is mscripten. So mscripten is essentially the compiler that compiles C++ to WebAssembly. In this case, I'm using ASM.js because setting up WebAssembly was a bit of a hassle, and it's irrelevant. What gets executed is exactly the same thing, just that WebAssembly is very compact, and the compiler can load it way, way faster. But the thing that gets executed is the same. So now we are compiling the C++ program again, you see .cc, into JavaScript with mscripten. And now we run it. And it's slow. Why? Well, because we didn't optimize that. C++ compilers. You need to tell them to optimize the code. And now we run it. And Now it's much better, really better. So if you do the ratio, we run the other again, it's more like 1.2 the ratio. So now it means that we can really get to C++ like performance if we put the proper effort into doing that. And actually, we could use typed arrays, and it gets even better. And we can fix the algorithm, and this is tricky. So now I'm cheating. In that algorithm, we were essentially iterating the whole bunch of primes. Now, mathematically, you cannot have a number that is larger than your square root as a divisor. So if you fix the algorithm like that, with this kind of patch, so you do the square root and limit with it, then you run it, and you have 100 milliseconds. Which means, know how to optimize your code, but know how to pick the algorithms. Because if you pick the wrong algorithm, everything you know about how to optimize code is totally useless. Okay. Now the ratio is sort of okay-ish. And now this is 50 times faster. So we got 50 times faster as before, by changing the algorithm, of course. Now I have another small project. And this project is essentially, it's like a grid. I was thinking something, okay, in the beginning it had to be something resembling a grid where you can move around, but thinking about it, it could resemble a neural network in some way. So it's a grid of cells. It's an array of arrays, so it's a matrix of 2000 times 2000, and essentially every cell contains an object, and this object has the coordinates x and y, and then there is up, down, left, and right. So every cell has references to the other 4 cells. This is the gist of the code. And the code essentially builds this and assigns all the references so that you can actually work with this thing. This is just a bunch of code. Okay, I run this code, and it takes almost 3 seconds. Now, I run a modified version, which takes 2.3 seconds, and the diff is only this. You can see the new array, I passed the size. So in the code before, I had the constant for the size, but I created the array, and the just-in-time compiler was emitting code that was growing the array over time. Now the array is pre-allocated, and since it's smallish, it's just 2000 elements, it's okay. And I have that speed difference just for this. So from 2.9 to 2.3. Now there is another version of the code that is 1.6. And in this version, the difference, besides the size, is that I added those 4 assignments. Those 4 assignments are for the rule that the object needs not to change shape. So I create the objects. I still don't have the references to the others, but I pre-allocate the properties anyway, and then I assign them. And you have seen that I go from 2.3 to 1.6. So the thing I was telling you before, they really matter. So if your code is CPU bound, do these things. They matter a lot. Now let's try C++. I have a C++ version of the code, but I must admit it, I cheated in the other direction. So in C++, it takes 94 milliseconds, which is shattering. Why? Because in C++, I use C++ like it is meant to be used. In JavaScript, I have this array of arrays, and each array has references to objects. There is no real way to inline an object inside an array. So you need to write it like that if you want to write proper code, I mean understandable code. While in C++, you have no problems. You can just write a huge matrix with the objects embedded in the matrix. You have control, low-level control over the memory. So I wrote the C++ program. It's essentially exactly the same, the code, but it does this trick at the beginning. it's like you probably would do for a neural network. So you have the full matrix and you work inside. And well, it's fast. Let's go and script them. Because at this point, I say, okay, I cannot do that with JavaScript. I try. And so I compile it. I need to give it a bunch of memory. And then I run it. And it's 96. And you get it? So this is unscripted. Which means that probably what I said at the beginning, probably it's feasible. If you know what you are doing, you can take a C++ engine for computing neural networks, and you can embed that inside the JavaScript application. You just need to be a bit careful. Okay, that's all. Questions?